In this video, we're going to introduce an idea that'll be new to most of you. It's the idea of trigonometric ratios. And we'll define what that is in a minute. But first, let me kind of set this idea up by taking a look at three triangles that are all similar. So here you can see I have three triangles, triangle ABC, triangle DEF, and triangle GHI. And I know that all three of these triangles are similar by angle-angle similarity. I can see that they all have a 32-degree angle, and they all have a 90-degree angle. And that's important that these are all right triangles. They all have a 90-degree angle in them. So let me just write down that I have triangle ABC, which is similar to triangle DEF, which is similar to triangle GHI. And again, they're all similar by angle-angle similarity. Now, the next thing I'm going to do is I'm going to compare a couple sides between these two triangles right here. And to make things easy to visualize, I'm going to color code the sides that I'm talking about. So I'm going to be looking at segment BC and segment AC. So I'll color segment BC, I'll make green, and segment AC, I'll make this purple color right here. And I'm going to be comparing those to segments EF, which I'll also make green since it corresponds to segment BC. And then segment DF, which I'll also make purple. Now I know that by the definition of similarity, I should have proportional side lengths between these two. That if I pair up BC and EF, so if I make segment BC in a ratio with segment EF, that should be equal to segment AC in a ratio with segment DF. All right, I know that this proportion should be true based on the rules of similarity. Now, I'm going to take this and I'm going to rearrange the parts of this proportion. You'll see what I'm going to do. I'm going to cross multiply and then I'm going to do some dividing. So it's going to turn into this. I'm going to have segment BC get multiplied by segment DF, and then that's going to equal segment EF multiplied by segment AC. And then what I'm going to do is I'm going to divide both sides of this. I'm going to divide both sides of this by AC times DF. I think that's what I'm going to do. I'm going to take both sides of this and divide by AC times, let me write that in the same colors. I'm going to take both sides of that and divide by AC times DF. AC times DF. And then I'm going to have some canceling that happens. The DFs will cancel out here and here. The ACs will cancel here and here. And so what I'm going to be left with is a proportion that now says BC over AC equals EF over DF. And so you can see the difference is in this original proportion, I was comparing segment BC from this triangle to segment EF from this triangle in my ratio here, and then my other ratio was taking a side from the smaller triangle and pairing it up with a side from this medium-sized triangle. So that was the first proportion I had. And then just by some mathematical manipulation, what I ended up with is a proportion that compares the two sides on this triangle, BC and AC, and says that that ratio should equal the ratio of these two sides on this medium-sized triangle, EF and DF. And now it's not too much of a leap, it's not too hard to kind of visualize that if I did that same thing with this largest triangle down here, so I'm going to color segment HI the green color, I'm going to color segment GI the purple color, and now if I have this triangle, which again I recognize that these three triangles are all similar, I can actually also include a ratio that would say that HI over GI would be equal to these other two ratios. Or in other words, for each of these triangles, if I made a ratio between this green side and this purple side, that ratio would be equal in all three triangles. Now I could also do a couple other similar things. Again, I chose, way back at the beginning, I chose to use these two sides of these two triangles, right? BC and AC, EF and DF. I could have very well chosen to use maybe segment AB instead of perhaps segment AC. And so if I use segment AB, segment DE, and segment GH instead of the purple segment, then I would have had another set of ratios that would be equal, that would say BC over AB equals EF over DE equals HI over GH. And so my point is this. My point is that if I pick out two sides of this triangle and make a ratio out of them, maybe it's the green side and the purple side, maybe it's the green side and the red side, maybe I could have done the purple side and the red side as well. But if I pick out two sides of this triangle and make a ratio out of them, that ratio should be equal to a ratio of the same two sides in these other two triangles. So if I compare green and purple for all three triangles, all of those ratios should be equal. If I compare green and red in all three triangles, those ratios should be equal. I could compare purple and red in all three triangles, and those ratios would all be equal. And that idea there is the concept behind what this video is all about, which are these things called trigonometric ratios. So let's take a look at what a trigonometric ratio is. So here we have a few definitions of trigonometric ratios. First of all, when we talk about a trigonometric ratio, or a trigonometric function, they're called sometimes, they're ratios that compare side lengths of a certain right triangle, and they connect those side lengths, they relate those side lengths to the measures of the acute angles in that triangle. And that's a little hard to wrap your head around, so let me just jump in and tell you about the three ratios. They're called sine, cosine, and tangent. So when we say sine, cosine, and tangent, we're usually saying the sine of one of these angles in this triangle that's an acute angle. So we're not necessarily going to say the sine of angle C, because angle C is the right angle. We might say, let's look at the sine of angle A, or let's look at the cosine of angle A, or let's look at the tangent of angle A. Or we might say, let's look at the sine of angle B, or the cosine of angle B, or the tangent of angle B. And we say that. When we say let's look at the sine of angle A, what we mean is let's compare in a ratio the length of the opposite leg from A to the length of the hypotenuse. So let's talk about those terms, opposite leg and hypotenuse. We know that every right triangle has two legs that make up the right angle and a hypotenuse that's across from the right angle, right? So every right triangle has two legs and a hypotenuse. When I'm looking at angle A, one of those legs is going to be across the right triangle from it. We call that the opposite leg. You go from that, maybe from the vertex of that angle, angle A right here has a vertex at point A. If I go from that vertex across the middle of the triangle, then the side that I run into is called the leg that's opposite angle A. The other leg would be considered the adjacent leg to angle A. Adjacent means next to. So I think of it as the leg that's next to the angle A here, right? And then you have the hypotenuse, which is always the side that's across from the right angle. So if I want to look at the sine of angle A, I would be looking at a ratio or a fraction where the opposite leg side length is on top and the hypotenuse length is on the bottom. So for this particular triangle, the sine of angle A would be the length of BC over the length of AB. And this, by the way, is the abbreviation for sine. The full word is S-I-N-E. We take off one letter to make its abbreviation. And so it looks like sin, but we don't pronounce it sin, we pronounce it sine. So when you see this, we say that as sine A. So sine of angle A would be the ratio BC divided by AB. The cosine of an angle is a ratio that takes the adjacent leg length and divides it by the hypotenuse length. So the cosine of angle A would be the length of AC divided by the length of AB. And that's cosine. An abbreviation for that is just COS. So when we see that, we don't say cos, we say cosine of A. And then finally, we have the tangent ratio as well. The tangent ratio of an angle is a fraction with the opposite leg on the top, and the adjacent leg on the bottom. So the tangent, we don't say tan, we say tangent of angle A for this picture would be BC divided by AC, opposite leg divided by adjacent leg. And those are our three trigonometric ratios. And there's a nice mnemonic device that people use to remember what sine, cosine, and tangent mean. It's called Sohcahtoa. Let me write that out. Sohcahtoa. And it stands for sine is opposite over hypotenuse. That's what SO stands for. SOH is sine equals opposite over hypotenuse. Cosine equals adjacent leg over hypotenuse. So that's CA, C-A-H. Cosine is adjacent over hypotenuse. And then the TOA part says that the tangent is the opposite divided by the adjacent. And so you're going to get real familiar with this phrase Sohcahtoa. It stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. All right? So this example over here all talked about the sine, the cosine, and the tangent of angle A. Well, what if we looked at the sine, cosine, and tangent of angle B? Let's look at that. Let's just kind of real quickly write out what would the sine of angle B represent, or what would represent the sine of angle B, what would represent the cosine of angle B, and what would represent the tangent of angle B. So we know that the sine of angle B is going to be the opposite leg from B divided by the hypotenuse. Well, if here's angle B, the opposite leg is now segment AC, right? It's no longer adjacent to angle B. It is opposite from angle B. So that would be segment AC. And the hypotenuse is still the hypotenuse because it doesn't change. The hypotenuse is always the side that's across from the right angle. So the sine for angle B would be segment AC divided by segment AB. The cosine for angle B says put the adjacent leg over the hypotenuse. Well, the leg that's adjacent to angle B is actually this one, segment BC, right? It was opposite angle A, but it's now adjacent to angle B. So when I make my cosine ratio, it would be BC over AB. And then my tangent ratio, which is opposite divided by adjacent, would be AC over BC. So just to compare for a second here, one last thing. You'll notice we had one triangle here. The three trig ratios for angle A are over here. Sine was BC over AB, cosine was AC over AB, and tangent was BC over AC. But then when I switched and looked at angle B, and I did the three trig ratios for angle B, something interesting happened. What was the cosine for angle A becomes the sine for angle B, right? Cosine of A was AC over AB, but that's actually sine for angle B. And the reason is because adjacent and opposite kind of switch, the labels switch when we change angles. What was opposite angle A is actually adjacent to angle B, and what was adjacent to angle A becomes opposite for angle B. And so the result is what was sine for angle A is actually cosine for angle B. What was cosine for angle A is actually sine for angle B, AC over AB. What happens to tangent is that the tangent for angle A and the tangent for angle B are reciprocals of one another. They're flipped over versions of one another. Tangent for angle A was BC over AC. Tangent for angle B was AC over BC. So this is the idea of trig ratios. We're going to be using this a lot in the next week or two as we move through chapter 8. This is the basic idea that when we say we're going to look at a trig ratio, we're going to say, okay, how does this angle, maybe angle A, maybe angle B, how does it relate to, what's the connection between that angle and some of the side lengths in your triangle? If we're looking at the sine of the angle, we're comparing the angle measure and the ratio of opposite and hypotenuse. For cosine, we're kind of connecting the angle measure to the ratio between adjacent leg and hypotenuse. And for the tangent ratio, we're connecting the angle measure to the ratio between opposite and adjacent.